Hello again, and thank you everyone for joining us for another session of our seminars on data science and AI. Today, I am deeply honored and glad to introduce a close friend and also a highly esteemed colleague of ours, Dr. Mo Haghighi from IBM. Dr. Haghighi is the leader of the Build Labs at IBM and also a former research scientist at Intel, a former Java and open source developer at Sun Microsystems. Mo has a PhD in computer science, and his primary areas of expertise are distributed and edge computing, cloud native, IoT, and AI, with several publications and patents in these areas. Mo led IBM's hybrid cloud build team in EMEA with a team of 100 plus developers, cloud architects, and data scientists in 9 markets across Europe, Middle East, and Africa. His teams enabled key strategic partners and ISVs to build multi and hybrid cloud solutions with OpenShift and Kubernetes across various public cloud platforms, including AWS, the Google Cloud Platform, Azure, IBM Cloud, as well as on-premise and private. Prior to that, Mo led the developer ecosystem group for IBM in Europe, where his teams empowered client and community developers to develop the skills they need to build solutions through hands-on workshops and co-create pre-sales MVP to accelerate their time to market. Mo is a regular keynote speaker at major developer conferences, including DevOps, DevOpsCon, Java Code One, Code Motion, DevRelCon, O'Reilly, The Next Web, and so on. Mo, thank you very much for joining us. I need to quickly refresh our audience's memory of the rules of engagement. Throughout the talk, please remain muted. If there is a question that you would like to ask, and it's a minor question, not something that requires longer discussion, please put it in the chat box. There will be time for Q&A at the end of this session. Also, please note that this talk is being recorded. And with that, and without further ado, Dr. Haghighi, the floor is yours.
Thank you so much, Wahid. It's a great honor to be here, and thanks for inviting me. Good morning, good afternoon. Thank you for joining my talk on real-world applications of machine learning with IoT and edge devices. My name is Mo Haghighi, and currently I lead IBM's Build Labs. My team basically, as Wahid said it perfectly, enables clients and partners to port their applications across public and private cloud platforms such as AWS, GCP, Azure, and IBM Cloud. We also help them enable their developers to develop the skills they need to build solutions with IBM's open hybrid cloud technology. So developers and data scientists in Build Labs will engage partners through architectural whiteboard sessions, hands-on workshops, and we also co-create pre-sales MVPs to accelerate their time to market and drive platform adoption by enabling them to build on top of Kubernetes, OpenShift, Cloud Paks, and IBM Cloud. I would like to start my talk by telling you a little bit about myself and my journey through IoT and edge computing. In 2007, I had the honor of working for Sun Microsystems, which was the pioneer of many revolutionary open source tools and technologies such as Java programming language, Solaris operating system, VirtualBox, ZFS, NFS, and Spark microprocessors. As a Sun ambassador, I worked with a group of over 500 developers across the world to build and promote open source technologies, mainly with Java programming language, NetBeans, and Open Solaris. Back then, Sun had an amazing IoT product in their labs called the Sunspot. And obviously for me, as an avid Java programmer and a big fan, I helped many young developers to program these small programmable objects, as you can see here, with Java, that inspired me so much that I decided to do a PhD in wireless sensor networks, which was followed by 2 postdoc positions in smart healthcare and a smart city, using sensor technologies again. Later, I joined Intel Labs to integrate machine learning into IoT platforms using Intel IoT devices, mainly Intel Edison devices. And that allowed me to explore many real-world applications of smart IoT and edge devices, which I'll explain to you later shortly. And now at IBM, I've gone a level higher to explore the endless possibilities of cloud platforms and microservices in commercial projects, and obviously as the backbone of all these amazing edge and IoT devices. So that was my journey basically from 2007 so far. For those of you who may wonder about sunspots, as I just mentioned to you, and I showed it to you right here, here's a brief overview of what those devices offered back then. IoT developers could build network of hundreds of these devices using a simple SDK and APIs. And this small IoT platform enabled them to put all those amazing ingredients of an IoT network together in a very short amount of time. So, it has a sensor board with a row of 8 LEDs, an accelerometer, a gyroscope. It's got a temperature, light, and humidity sensors. And it's got a lot of IoT, I/O ports, basically, to connect your own sensors or servers or actuators, basically, for various applications. And it's all powered by a small battery, which for many applications could last up to a month, basically. And obviously, sunspots enabled me to explore many applications of IoT and realize the potential of network of smart devices. So I completed my PhD in one of the largest research initiatives in the UK called Large Scale Complex IT Systems, with many corporations involved in that initiative. And in order to mimic human behavior in smart devices, I combined auction-based algorithms and game theory to make IT devices both selfish and at the same time social for different scenarios where resources are scarce. So that's basically what I did for ARM architecture back in 2012. My latest project is a cluster of 125 Raspberry Pis, which is something I've been working on since 2016. I have used this platform for many applications, including stream processing, coalition formation, and federated learning, which is something I've been working on recently. So this platform's got 84 Raspberry Pi 0, 24 Raspberry Pi 3s, 8 Raspberry Pi A+ model, and 8 Raspberry Pi 0W, and 1 Raspberry Pi 4, which is basically on the bottom, taking control of everything. And later, I basically just changed the platform in order to have more Raspberry Pi 4 instead of Raspberry Pi 3. And everything is actually programmed with OpenJDK, which is the open source version of Java programming language. And just for you to know what it's like, these are just like small, as you can see here is a closer look at these devices. We've got a cluster of 4 Raspberry Pi Zeros on top of a Raspberry Pi 4. And on the sides, the Raspberry Pi Model A as the master of each cluster. And that's basically how they are organized in this cluster. And again, it's one of the things that I do as a hobby, and I really enjoy programming all these devices and just throw a task at them and see how they can actually implement and execute all these tasks together at the same time for different purposes. If I want to start my talk, I would like to focus on AI and edge computing. When we talk about edge computing, it is basically a distributed computing framework that brings enterprise applications closer to data sources. And that's the most important feature of edge computing. And when we talk about data sources, we are basically referring to IoT devices and local edge servers. So the purpose is basically placing infrastructure services such as compute, storage, and networking physically closer to the field devices that generate data. And then obviously the sort of advantages we get out of edge computing is, by being closer to the field devices, we get lower latency, we get quicker response, and that basically, allows us to process more events, which ultimately gives us the power of, bringing machine learning and integrating machine learning, powerful machine learning basically in edge devices and IoT networks. But again, the biggest issue is that the sort of gateway or edge device one can deploy to the field. And that is actually the most important aspect because of the resources they've got. No matter what sort of device you put in the field as your edge device, they're still not going to be capable of training and inferring complex models. And that's going to be the focus of my talk today and how we can actually solve that problem. But before that, I would like to give you a quick overview of the sort of real world application we had back at Intel here in London as one of our top projects, working with some of the top academic institutes here in the UK and across the board. So we wanted to channel AI into IoT networks, and that gave us this opportunity to deliver use case inspired basic research activity to demonstrate the compute fabric needed to support the design of an urban Internet of Things, or IoT, for a smart city. And one of the most important aspects was basically this topic that we refer to as billion device challenge. And obviously later we focused on the citizen engagement and obviously creating a sustainable ecosystem. But for the purpose of this talk, I'm just going to focus on that billion device challenge and what it basically offered. We chose Queen Elizabeth Olympic Park in London, which was used as the venue for the Olympic Games back in 2012. And it is like a mini city within a city. And the reason for that is because we've got the stadiums, we've got sport venues, residential areas. We've got a river going through this park. We've got so many roads and rails basically going around the park. We've got a massive shopping center in there. And that gives us a lot of elements of a city that basically could have given us the sort of insight we needed to know when we deploy a massive IoT network into a city. And we could basically use this park as our sort of, demo area. And for the billion device challenge, communication was the most important aspect. We wanted to have all these devices out in the field doing various tasks, which I'm going to get to it in the next slide. But we had to have a system in place that all these devices were smart enough to know exactly what sort of medium they had to use for communication. Was it low power wide area network? Was it Wi-Fi, mesh network, cellular communication? And that was basically one of the biggest challenges we had back then. So, managing radio communications in densely populated network of sensing devices with all those elements of a city, including cars going around the park, many people with their mobile phones and devices basically walking through the park. And we had a lot of residential buildings there as well, which could have created a lot of interference. At the same time, we had the West Ham Stadium, in the park, and that basically brought thousands of fans to the park every week to watch the game or watch the team practice. And again, that created a lot of interesting challenges for us to understand the dynamics of deploying a radio communication network. So the first step for us was basically deciding on our main communication mechanism or protocol. So we used LoRa, which is basically a low power wide area network specification for battery powered devices. It is basically capable of communicating very small amount of data, very low rate, but at the same time, it gives you a very large sort of communication capacity in terms of the sort of distance the frequency basically travels. And that basically provided us with a lot of advantages because we installed this LoRa receiver on top of this amazing infrastructure structure in the park, which is called the Orbit, and it was like 114 meter above the ground, and it gives us a coverage of up to 22 kilometers, a radius of 22 kilometers to capture data from LoRa devices. And that's actually one of the most interesting aspects of LoRa communication. Just having this is amazing technology in the park gave us a lot of advantages. Just using a single receiver, which I installed it myself, on top of this is a structure to receive all this amazing data coming from different sensors that I'm going to tell you in a bit. And then obviously it was about the sort of device we wanted to build. So this device that we built as a sort of demo It was we used adaptive radio protocols to opportunistically route messages, adapting to dynamic applications. So for instance, for LoRa, we have different specifications like the spreading factor that had to be adjusted in order to bring down the noise and make sure that our bandwidth and throughput is actually saved and secure. So we basically created the small devices using Intel Edison. So as a research scientist, I had the opportunity to use Intel Edison for a number of applications and projects within Intel Labs with my colleagues in Dublin, in Santa Clara, Portland. And, for you just to know, Intel Edison is a tiny processor based on x86 architecture with dual atom cores and, 1 gig of RAM, onboard Wi-Fi, and Bluetooth low energy transceiver. So that basically was the sort of device we wanted to use for our IoT devices. So you could run Java, Python, C, what have you, and it has basically Linux, Debian, and Yocto on top of that. So you could easily run containers on top of these devices. So what we had to do was then later adding Wi-Fi, which was already included in our Intel Edison devices. We had BLE, but then we had to basically include a LoRa device and 802.15.4, Zigbee, for instance, in order to create a mesh network as well. So LoRa was for long distance communication. And at the same time, we had 802.15.4 for creating a mesh network across the park. And those devices that you see in this photo, they were like small boxes that, they were like waterproof, weatherproof, and we had to basically install these devices across the park. But the most important aspect was basically the sort of sensing we were doing. So we used microclimates such as humidity, temperature, solar and air pressure. There were different sensors in the box. And at the same time, we had water quality sensors connected to some of them around the river, because the ecologists in the park, they were interested in the pH level, oxygen level, and different types of, the ORP as well, of the water going through the park, because they wanted to know exactly what's happening, especially because there were like fish and other creatures in the water as well. And then bat species, the sort of bats that were traveling around the park or living in the park. And that was quite interesting, because the ecologists told us bats are very good indicators of biodiversity of an environment. And that created a big challenge for us, because we had to have sonar sensors in our devices to capture bat calls, and they're like humans. They have a stress calls, social calls. And then once we did that, we had to basically process this data based on the sort of model we already had, the trained model we had in these boxes, to say what kind of a species that bat is. And if they are happy, they're stressed, and that's a very good indication for a healthy environment or biodiversity of an environment for the ecologists in the park. So all these sensors, we basically connected them to these Edison devices, and we spread them around the park. And then we had the gateway. As I said to you, that gateway was a LoRa receiver on top of the orbit to capture all these signals coming from these devices. And then it was connected to a cloud where we could actually read all the data coming in, in real time. And that was quite interesting, because we had all these devices across the park. But sometimes, because of the noise in the park and people walking around the park and traveling, we had a lot of, dropout in the signal and, blind spots sometimes, that we had to actually solve the problem. Because sometimes when there were fans traveling, to the stadium in the park, we couldn't basically use Wi-Fi anymore, because all their devices were, occupying the 2.4 gigahertz band, and we had to actually move on to another band, and which was basically gave us the opportunity to go into LoRa to send and receive data. But obviously LoRa was only good for low throughput data, so we had to basically only send metadata at that instance. And at some other time, we could easily just route data through another device, which could have had a better communication or lower SNR, as we call it. But then just to give you an idea about the sort of challenge we had, this is like a simulation using Unity of these devices basically communicating with the gateway. And as you can see, there were so many signals sent and received at different times of the day. And obviously that created a lot of noise, and at the same time created a lot of challenges for us on how to we could solve the problem. We had to make these devices very smart, to decide which sort of transceiver they've got to use at different times of the day, different days of the week, in order to have a higher productivity and throughput. So the biggest problems for us were like, for bringing ML into IoT devices, obviously we had to adjust all those dynamics and make sure that the latency, throughput, the energy that those boxes consume. If we wanted to use Wi-Fi all the time, obviously the battery in our devices wasn't enough for them to run all day. And obviously you had to adjust the data rate, signal strength, and packet error rate as well. So those were the sort of parameters we were looking at for using different communications. So this is a quick example of the optimization we did in the park. As you can see, on the right-hand side, we've got no signal. Basically, our signals are, it says NS, that means no signal. And those are basically receive signal strength indicator and SNR, signal noise ratio. And we wanted to basically improve that. By using some algorithms, we could at least get some of those devices back in the network by basically using some sort of optimization techniques that those devices were learning over time on how to communicate and what sort of communication protocol they've got to use. And that was just a very quick example of what we can actually do on small devices in order to improve the communication. But going back to what I mentioned earlier about edge computing and obviously, the sort of advantages we get out of it as a, quick reminder, then we come to the device. How can we use edge devices to run machine learning models? Are they capable of such tasks? Can they, handle both data gathering, training models, and making decisions in the field? And those are the questions that we should ask ourselves. But we've got to distinguish between the two types of operations for edge devices. One refers to training, and training means, process of creating a machine learning algorithm or model, and it involves like different deep learning frameworks, and you've got you've got to train your data sets, and obviously the IoT devices were the sources of all that data for training them and creating the model. Whereas inference basically refers to the process of using a trained machine learning algorithm, and that basically doesn't require a lot of power like the training. The training side requires so much power. You need more capable devices, bigger number of cores, as I'm going to get to it in the next slide. But inference basically is a much simpler process because you've already got your model trained, and all you need to do now is basically use that trained model to make a prediction. So when we talk about that, that's where the old debate between CPUs versus GPUs basically happens. Until 5 or 6, or sometimes you can say actually 10 years ago, we didn't even have a GPU in IoT devices or edge devices in the field. GPUs were mostly used in personal computers and resourceful systems. When we use CPUs, you can only get up to 24, 32 cores of CPUs, and a GPU basically gives us a far greater number of cores. And I'm going to basically mention a few GPUs available for edge devices. And obviously the high density of the cores of GPUs gives us a lot of parallel computing, and that's actually a fantastic sort of resource for both training and inference. But again, when it comes to training, you need a far more greater resources to train your model with that amount of data you've got available. One example for inference, basically, you can use TensorFlow Lite, for running machine learning models on mobile devices such as Raspberry Pis, your Android devices. You can even, run it on BeagleBone, or even smaller devices like, Raspberry Pi Zero. Even that is actually possible to do that. But obviously, that's for very small models that you've already trained, and it doesn't take much heavy processing to do that. But obviously, if you want, more capable devices like, Jetson devices from NVIDIA, you've got really good amount, resources in terms of memory, in terms of the sort of CPU you've got available, the number of cores, for instance, GPU cores you've got available in TX2 devices. And again, they've even been revised, and there's a new version of that updated with, I think, more than 500 cores, CUDA cores available. And then if you obviously go into more capable devices, such as, Jetson Xavier, you've got really good number of GPU cores, but at the same time, you've got multiple CPUs to take care of different tasks in your system. And then when it comes to storage and RAM, it's just amazing how much you can actually do in the field using these devices. But again, when it comes to training models, you can obviously use TensorFlow, you can use OpenCV, Keras on these devices, but how much time do you have basically to train your model? It's very it's a very data intensive and process intensive sort of process for you to train a model in the field. And again, many applications, they decide not to train their models in the field. So the next question is, for edge computing, where should it happen actually? You've got your edge computer that you don't want actually to do all the training on it because it's not capable, but then you've got cloud. Using cloud, you can do a lot of things, but again, at the same time, you get latency, and you've got a slower response to certain events. So you've got to basically decide what to do. And the answer to that is you've got to always combine them. And I'm going to get to that in a bit. But let's focus on the cloud side. If you use cloud and you've got a very good internet communication in the field where you've got your devices deployed, you can easily use a quick auto AI on IBM Cloud basically to just deploy your upload your data in CSV and build your model, and then just run it in the field. That's quite simple, and you can easily do that. And then obviously the sort of resources you get in a public cloud environment is endless. You've got so much power, so many GPU cores, so many CPUs, RAM, and obviously you've got so many APIs at the same time available to you. But the question is, do you have that internet connectivity all the time, or do you only have it for a certain time of the day, or you don't even have enough power in the field to run a device that is capable of communication on a high bandwidth? And as I said earlier, the answer is actually using hybrid cloud model. So with hybrid cloud model, you can basically train your model on a public cloud and then move that model onto your edge computer and then infer that model in your edge device. But at the same time, the more data you gather in the field, you can, at certain times of the day or, week, or, depending on your application, you can always upload that data to your public cloud environment and make your model, optimize. That basically is one of the sort of models that I can see a lot of enterprise, applications are using at this time. So they try to have this hybrid model. So training in public cloud and then inferring at the edge on your edge computer. But the question here is, when you want to do that, why do you have to what would happen to your application? Do you have to basically build your application twice? Or can you, build your application once and deploy it into your public cloud and your edge computer? Sometimes you want to run your applications on both devices. When you don't have connectivity, you can easily shift your workload into public cloud. And when you have you don't have internet connectivity, you can actually bring it to your edge computer. So the biggest question is, why do you need hybrid cloud model? And again, the sort of motivations for hybrid cloud is different. When you talk to, the motivations for having multi-cloud applications, in our conversations with our clients, basically, depending on whom we are talking to, motivation for multi-cloud are subjective. Cost reduction is always that common reason in a majority of our conversations with business execs. But that one aside, C-level execs are mostly interested in providing business flexibility to their clients and delight them with new and competitive features. Developers are looking for ways to expedite their journey from development to testing, staging, and production. Operation engineers are motivated to simplify the operation, increase the security, which is a very important aspect, and obviously reduce the cost. But for the last decade or so, we've got this new team which is called DevOps, and it sits somewhere between developers and operation engineers. For DevOps teams, portability is number one factor, and that basically goes back to the point that I raised earlier: building your application once and being able to port it across different devices and different public cloud environments. So going back to that portability, we've got three different types of portability. One is about the application itself. The other one is about the workload. Let's say we are dealing with a scenario where your workload is suddenly increasing and you want to actually be able to shift it across different cloud environments or different devices. So that workload portability is very important, having that capability in place. And then sometimes it's about the functional, functions and services portability. Some of your services can easily run on your edge devices, like the inference of your models, and some of your functions are only good for public cloud. So you've got to be able to run all these in a hybrid manner without causing any sort of interruption, and also increasing the cost for the development of your applications and deployment of your applications. The sort of models we have is either between different public cloud environments or between private and public clouds. And a lot of corporations basically decide to have private clouds because they want to take advantage of public cloud for certain types of applications where confidentiality and privacy is not a concern. And the ones that they've got their customers' data, they'd rather basically run those models on their private cloud. And again, it's all about matching the right workload to the right cloud environment. Different cloud providers, they've got different specifications. I'm not going into details of which one is better. Obviously, they've got different, services. Their compute model is different. Their instance provisioning time, is different. Again, for some of the applications, time critical applications like finance and the stock market, you always need to rely on a cloud that has a, faster provisioning. Some of them, they've got a higher downtime. Some of them, the cost is different, or the type of billing you get is different. But again, all these figures are changing all the time and nothing is actually certain. But when it comes to IBM Cloud, we've got your enterprise ready. We've got all the different types of cloud options. In terms of industry specific sort of models, we've got vast expertise across different markets and verticals. And then when it comes to the available data centers, we've got over 60 data centers across the world. But the most important aspect when I speak with our clients and their developers is actually the security aspect of IBM Cloud. They always refer to the all-round security features of our cloud platform as number one requirement for their firm. And that's why we've got 47 out of Fortune 50 basically relying on IBM Cloud. As I said, it's all about matching the right workload to the right cloud environment for your business. And I don't think any cloud is better than the other. It's all about matching and having that capability in place to be able to port your applications across different clouds. But that takes us to a very important concept. How can we design an application that can be updated continually without downtime? Different teams can own and evolve different services, and our applications can be migrated from one cloud platform to another seamlessly. And the answer is cloud native development. That's the model you need to follow. Cloud native refers to how an application is built and deployed rather than where the application resides. And it basically defines that the application must be built, delivered, and operated in a way that it is not hardwired to any infrastructure. That's a very important aspect. So once you have that model in place, the cloud native development model, then you can actually port your application and workload across different cloud environments. And then how does cloud native development makes those happen? Simply by relying on microservices architecture. Microservices architecture is the building block and the most essential ingredients of cloud native applications. A cloud native applications consist of discrete, reusable components known as microservices that are designed to integrate into any cloud environment. Microservices architecture addresses all the liabilities that are inherent in monolithic applications. And I'm going to get to monolithic applications later. But microservices architecture advocates partitioning large monolithic applications into smaller independent services that communicate with each other or using HTTP and messages. And that's a very important aspect for those who are designing AI applications. You need to design them as microservices in order to make them scalable and portable. Let's take a look at this application as an example. On the left-hand side, we've got these monolithic applications for a storefront, and you can see that you've got the catalog, you've got the billing and everything, all the other services, recommendation services, all bundled up as one basically monolithic application. when a service goes down, the entire application could easily go down, and it becomes, unresponsive to your clients. Whereas, with microservices, you partition your application based on business functionalities. Your cloud service, your catalog service, your recommendation service, inventory, and your billings are completely separated. If one of them goes down, that doesn't necessarily mean that the entire application will go down. So this basically gives you highly maintainable and testable microservices, loosely coupled microservices, and independently deployable microservices. And they're all basically organized around business capabilities. So if I want to show you one quick example, in this application, monolithic application, you've got analysis, data parsers, user interface, and these data visualizations all basically bundled up as one monolithic applications. If one of them goes down, they're all going to go down. But we can easily turn them into microservices by cloud native development. So you've got different basically services in different programming languages or technologies or platforms, all working together without causing any interruption. And that gives you a number of advantages, as I've been telling you over the past couple of slides. Services can evolve on different timelines. Services can be deployed separately. You can actually choose your technology, like what you saw, like Java, Python, different programming languages, different platforms. You can easily use different frameworks and combine them together without causing any issues to any other members of the team, or everyone basically having to follow the same programming language. And at the same time, you can scale individual services dynamically. You don't have to scale the entire application. You can just scale individual microservices where you've got a higher load, basically. And the most important aspect is, if a single microservice fails, the overall application remains functional. So what you need to do is you need to containerize all these microservices with their dependencies and libraries. And that gives you a cloud native approach to your application. In the monolithic applications environment, you have a number of issues that make applications prone to failure, make them difficult to update, and often hard to identify where the errors basically occur. Because monolithic applications are designed and operated as a single entity, if any part of the application fails, the whole application becomes unavailable or unresponsive. And that's basically the destination for monolithic applications. They're all destined to fail. So for those reasons and many other reasons, we now need to focus on how we can actually orchestrate our microservices. How are we going to orchestrate our microservices is scale them based on demand and recover from failure. Make updates to the microservices without causing interruption. If you want to go one by one, obviously that's going to become very difficult. And that's where Kubernetes comes into play. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. What does Kubernetes offer? A multi-container application must run on a multi-host environment in order to eliminate that single point of failure that I mentioned earlier. If one host went down, our orchestration tool can switch the load to another host. We need to be able to create new instances of our individual microservices containers to scale accordingly. When one or more of our services need to be updated, or let's say we are adding a new feature or a service to our mix, the orchestration platform must be able to automatically schedule new deployments and create new instances of our containers with zero downtime. And then it basically comes to Kubernetes is scaling and managing our containers according to the available underlying resources on the host. As I said earlier, the resources we've got available, that needs to be taken into account. But if you build your application for public cloud and suddenly you put it on an edge device that doesn't have enough memory or CPU cores, then obviously your application is going to fail. Kubernetes can easily detect that and make sure that whatever is going to be thrown at your application is actually based on the available resources. And last but not least, Kubernetes checks our containers continually to make sure they're healthy. And in case of any failure, it will basically take actions to reinstate our deployment and create new instances or restore the services. So it's always we state what we desire about our application, such as the number of instances of individual microservices and allocated resources. And Kubernetes basically observes the actual state of our application and will keep on adjusting and adjusting our resources to make that happen. So it is that continuous reconciliation of observed and desired states. Now, let's take a look at our deployment scenario on a higher level and how we are going to deploy our application on Kubernetes. We broke down our applications into microservices and containerized them with Docker in this case. So deploying each Docker container with Kubernetes will spin up a pod with its Docker container in there. And based on our deployment scenario and the load, each pod gets replicated. This is very important. Gets replicated with the number of replicas. And that's basically how we are going to make new instances of our Docker containers. So first we created a deployment, then we scaled our deployment accordingly. And then we need to create a service which allows our applications to communicate with each other, or our microservices within a cluster, and later exposes our applications to the internet and external networks. These are basically 12 Docker and kube control instructions that I'm going to basically show you, what would happen within Kubernetes. So first, we build our Docker file in order to containerize our microservices. And that takes a quick Docker file that you need to actually say where this is coming from, what is this image about, what are the parameters in order to run this container. And then you need to use Kubernetes basically to run each of those commands, basically to create a deployment, to expose that. So all those processes that I showed you demonstrated, you need to basically have those commands in place. And that takes almost 12 basically steps to do that. And if we are dealing with batch operations, in most cases, we need to craft a YAML file to describe the task we want to implement in Kubernetes. Except a few options from Kubernetes dashboard, all monitoring and logging basically needs to happen within CLI. And that's basically quite difficult because you need to remember all these commands. And if you want to look at it, what would happen in the background, I don't want to go into details, but here's what's happening. Use kubectl, which is your magic word, or kube control as they call it, to communicate with your master node. Your master node communicates with your worker node and creates all those pods through kubelet. And then you create services using kube proxy. So as we have seen, learning Kubernetes commands, having to containerize microservices, and working from a command line interface are not ideal for developers and AI application developers who want to focus on coding and the logic of their applications and enhancing their applications. And that takes us to OpenShift. And that is very important. Red Hat OpenShift basically is built on top of Kubernetes, brings along all the brilliant features of Kubernetes, but it bundles Kubernetes with some essential features that will ultimately provide the best experience to both developers and operation engineers. How does it achieve that? Through a number of automated workflows that you can see in this diagram. Those automated workflows are a result of these components here. Kubernetes is wrapped around an enterprise-grade Linux operating system, networking, monitoring, registry, and more importantly, authentication and authorization services. And that gives you a fantastic environment, for both IT, operation engineers and also developers to deploy their applications and manage them automatically. So that gives us three key important features. One, you as a developer, you want to get started on coding as quickly as possible rather than learning, about different commands and platforms and tools. OpenShift comes with pre-created quick start application templates to build your application. Whether you have Java, Python, what have you, you can easily get started immediately because they're already pre-created quick start applications. The second one is obviously you want to focus on coding and not worrying about what's going to happen in the background. So you can just commit and push. And I'm going to show you in the next slide how that happens. You don't need to do anything else. All you need to do is just point your cluster to your GitHub. And then last one, you want to build and test your application locally. If you want to do that, you don't have to have a public cloud environment. And that basically is code-ready containers. That is the local version of OpenShift on your machine that you can easily test your application and deploy to see what sort of problems it might have or how you can actually make it better. So as I said to you, there's this amazing feature in OpenShift called S2I, or source to image. So building your image, deploying, and continuous integration is all going to be taken care of by S2I. So all you need to do is point your OpenShift cluster to your Git, and the rest of that is going to be, and then just commit, push, and that's it. All you need to do is just working with your Git, and the rest of the process is going to be taken care of by OpenShift. And you don't even have to go and learn all those CLI commands that you do for Kubernetes. When it comes to developer features, I'm just going to basically give you a quick summary of all those. First of all, in OpenShift, you've got a web console. You can easily just navigate through web console and implement almost all tasks from a simple graphical interface. You can build, deploy, update, and almost implement any task in two separate perspectives for both developers and administrators, let's say the operation engineers. With Kubernetes, it's always CLI, depending on whose Kubernetes services you're using on what sort of cloud platform. And then Kubernetes offerings differ from one platform to another. Almost every major cloud provider offers a different flavor of Kubernetes. You get different sets of add-ons, plugins, and set of instructions for connecting your application to your cloud resources, which in most cases are only applicable to that particular platform. With OpenShift Container Platform, your experience and the way you interact with the platform, let's say the OpenShift console, stays the same. Therefore, building, deploying, and managing applications with OpenShift Container Platform is truly build it once and deploy it anywhere. And last, Kubernetes is an open source project, whereas OpenShift is a product based on an open source project, which is Kubernetes Origin Distribution, or OKD. Comparing Kubernetes with OpenShift is like that classical example of comparing an engine with a car. With an engine, you can't do much. You can't go from A to B, whereas with a car, you just sit in and start driving. And that's basically what OpenShift offers you. And obviously all these amazing, sort of releases and quarterly releases and security patches, they all come with OpenShift. And the last important thing that I want to tell you basically when it comes to edge computing is IBM Cloud Satellite. So you can basically deploy and run apps consistently across on-prem and edge and public cloud environments from any cloud vendor. So you basically have to build your application once, and you can easily deploy it across from your public cloud into a small device, let's say Intel Nukes, for instance. This is a great example of that. You can find it on YouTube, and easily you can move your applications. Let me give you one example. So there's this amazing client in Los Angeles. So they've got this construction site that they want to have all these cameras around the environment to look for hard hats. They want to make sure workers without a hard hat, builders, they can't actually enter the site. And in order to do that, all these cameras, they need to have the capability of detecting them and sending an alert to the security to make sure that they're not getting access to the environment. If they want to use a cloud environment, the sort of latency, the time that it takes for this model to be checked for the photos that are sent to the cloud environment is going to be a long time. And by the time the results come back, that person might be already on site and something might have happened to that person. So what they do, they use basically IBM Cloud Satellite to move their applications in, at the edge in order to basically detect those quickly. And the same application, the same client that we work with, they use the same application to detect masks when, during COVID-19. And that basically helped them a lot to make sure that everybody's wearing a mask on site. If you want to learn about, since the topic of my talk is about cloud native, and we've got a great panel of speakers basically teaching you everything in this sort of portal, I really encourage you to go and check out the Build a Smart on Kubernetes World Tour. We've got so many great speakers and great videos basically showing you how to build and deploy your applications on OpenShift and Kubernetes. I've also got my own courses. It's about 8 hours of courses basically showing you how to build, basically giving you all the details of microservices and how to build and deploy on Docker, Kubernetes, OpenShift, code-ready workspaces, code-ready containers, and later on how to build your pipeline and CI/CD pipeline basically. So you can go on my GitHub, github.com/Haghighi/COVID-19 web application. That's an application that I built during the pandemic just to basically retrieve data about COVID-19 from Johns Hopkins University repo in order to play with that data and apply different algorithms on them. With that, I want to thank you for listening to my talk, and I hope that you found it useful for your applications that you're building. Thank you.
Mo, thank you so much. This was such a wonderful presentation, and it was like one of those movies that you never wanted it to end. Every slide of your presentation was so informative. I know that you have another engagement starting in about 10 minutes.
That's right.
So our Q&A will need to be brief. I'm going to, again, exploit my role as a moderator to ask the first question. But in the meantime, if others have questions, please either send it over the text, the Zoom chat, or raise your hand. Mo, at SAIL, we are essentially interested in where things break, and that includes the assumption that microservices as an architecture are always better than monolithic applications. Have you come across any cases where the monolithic architecture wins over microservices due to perhaps communication overhead, due to regulatory constraints? Or as part of this question, I also want to ask you whether Kubernetes or any microservices engine or platform has been verified or is compliant with the requirements of essentially an RTOS substrate, a real-time operating system substrate.
Sure. So the first part of your question, obviously, adding more microservices requires a larger number of developers, who need to take care of each one of those microservices. So that makes it more complex from that perspective. And you need to have more sort of agile kind of approach to your application development. The different teams need to evolve different applications on different timelines. And that creates some sort of project management overhead, basically, on top of those, applications and microservices you're building. So apart from that, obviously, you need to have, a more scalable environment. But obviously, running multiple microservices, you need to have multiple environments, and that requires a multi-tenant environment, for staging, testing, and production. Let's say you're developing, testing, staging, and producing, basically putting the code into production. So that creates a little bit of complexity. But when it comes to, when I speak with our clients, the sort of advantages they're getting out of microservices and cloud native development is far greater than all the disadvantages that come with it. If it is an investment that helps them a lot in the future, because if your application is cloud native, if you want to add new features and new services, if something goes wrong and you want to detect immediately what's happening in the monolithic environment, it's really hard. It's going to take you far longer, basically, to detect and identify exactly where the problem resides. And nowadays, most of our clients, they're really concerned about that sort of delay that happens when their services goes down. Like, let's say we are working with a retail client, and during Christmas time, obviously, they've got more than 30x number of visits to their portal. And if something happens, they don't want their portal to be down for 2 or 3 hours, because they're definitely sure that their customers are going to go and buy their stuff from someone else. And for that reason, they want to definitely be able to get back that service up and running immediately. And one of the essential sort of qualities of cloud native development is that when a service goes down, you know exactly which service went down, and you can always go to that team immediately and say, look, your service is down. Customers can easily browse the catalog, but obviously the billing is not working. So you get that up immediately, or have that sort of blue-green deployment, some sort of kind of backup to bring it into production in order to get that problem resolved. So with microservices, adding new features, recovering from failures, all those things are basically going to be much easier. But obviously, you need to invest. You need to have a bigger team. You need to have far greater skills and diversity in your developers. And that basically requires investment. So I would say investment is number one. But again, for simple applications where you can actually bundle up your microservices, I would say that is easier, to use monolithic applications. But a lot of applications I'm dealing with our top clients, they're very, very complex. They're multinational. They're running across multiple countries and markets. So they need to have a cloud native environment.
Thank you for that wonderfully detailed answer. We have many questions. Those are sent to me as private messages. So I'm going to go with one of those from my PhD student, Binesh, who is also an R&D engineer at Medtronic and is dealing with a similar kind of context and problem. He asks, in a distributed wireless sensor network with machine learning on the edge, what are your thoughts on ensuring data quality, especially with degradation in perception layer or over time?
So what I can answer in this for this one is basically adding a microservices, adding a separate microservice to look after your data quality, to kind of validate that, verify that. And that's usually the sort of job that data engineers need to take care of. There's this new job. If you look at the market, there's always been data scientists. Nowadays, they're looking at data engineers. You need to have the right source of data. You need to have the right format for your data. Compliance, can you actually use that data? In terms of privacy and confidentiality, all those checks, data engineers basically are in charge of that. And what I can tell you is I can see a lot of new applications being developed for that purpose by data engineers to make sure that your data is verified and validated before it gets to your application for training. And that's basically a separate service, which again, cloud native development gives you the option to inject that immediately without refactoring your entire application. In the past, you had to refactor in your entire monolithic applications in order to do that. But now you can have multiple stages of microservices within, your environment, between your different microservices to check those, compliance or let's say validations. And again, I hope this answer is good enough. But again, it's a very long answer if I want to tell you, like in oil and gas is different. In banking is completely different. In healthcare is the most complex problem when it comes to this. So I hope you find it useful.
Mo, thank you so very much. We do have other questions coming in, but I don't think we'll have time to answer those. Would you be okay to respond to some questions offline if our audience reached out to you via email? And absolutely. Mo, you introduced your own course as well as a wonderful resource, the Kubernetes World Tour. I will be sharing the links to those later on the event page at SAIL. If you go to www.sail-lab.org, you'll see an event page for this presentation. Mo, we treasure to have had the opportunity to learn from you. It was wonderful to hear about your experiences and your thoughts on microservice architectures. And I believe that the audience have benefited at least as much as I have. Thank you so much.
That's very kind of you.
And hopefully we'll keep the connection and communication going.
Thank you so much, Wahid. The pleasure was mine. And again, thanks for the invitation and the opportunity to speak with your amazing students and researchers at New Haven University.
Thanks again, Mo. And thanks to everyone who attended the talk. The recording of this presentation will be posted to our YouTube channel and our website. We will have another presentation in 2 weeks by another esteemed colleague. The announcement will be sent out in the next week or so. Once again, thank you, everyone, and have a great Friday. Have a great weekend. Goodbye.